So in this problem, we need to first solve a logarithmic equation and then sketch the graphs of the left-hand side and the right-hand side and understand if our sketch is consistent with the obtained solution of this equation. So the equation appears to be very simple. 3 plus log x base 2 equals log base 2 of 3 plus x. I would like to first move log x base 2 to the other side, i.e. I would like to add to each side negative log x base 2. That is, of course, an equivalent transformation, so the solution set won't change. I can write the equivalent symbol. 3 equals log base 2 of 3 plus x minus log base 2 of x. This here is equivalent to a whole system of conditions. Because I would like to transform this difference of logarithms using the well-known rule log x base a minus log y base a equals log base a of the quotient x over y. But remember that here we require, of course, that the base a be positive and different from 1, and also that both logs on the left must exist. In other words, x must be positive and y must be positive. So we require that in this difference, both 3 plus x be positive, x be positive. And now we can apply the rule about the difference of logarithms. 3 equals log base 2 of 3 plus x over x. Again, it's very important that you don't forget these two things, because if you do forget them, you in general don't get an equivalent equation. Here, both 3 plus x and x are allowed to be negative. There's nothing wrong in the expression log base 2 of negative 3 over negative 4, because that's really log base 2 of 3/4. But you can't write that this will be log base 2 of negative 3 minus log base 2 of negative 4, because this doesn't make sense. So when you apply rules of logarithms, you always have to make sure the expressions involved actually make sense. Now we work with this system of conditions. What about the two inequalities, x greater than 0 and 3 plus x greater than 0? Of course, x greater than 0 is stronger than 3 plus x greater than 0, meaning that whenever x is greater than 0, it certainly follows that x plus 3 or 3 plus x is greater than 0. It's not true that 3 plus x greater than 0 implies that x greater than 0. So we see that this condition is stronger than this one, meaning that whenever this is true, this is automatically true. So we may neglect the condition 3 plus x is positive and forget about it. Now, with this equation here, we may raise 2 to each side of this equation. That'll give us an equivalent equation. Remember that whenever you have equality f at x equals g at x, that is equivalent to a to the power f at x equals a to the power g at x, provided, of course, that x is positive. Well, if a is 0, if a is 1, I guess a is not 1. So that is exactly what we're doing here. We are raising each side. We are raising 2 to the power of each side of this equation. 2 to the power 3 equals 2 to the power log base 2 of 3 plus x over x. The point of doing so is, of course, to get rid of log base 2, because 2 to the power log base 2 will be just the power 3 plus x over x. That is because, by definition, a to the power log base a of b equals b. By definition of logarithm, log b base a is the power to which a needs to be raised to get b. Here, of course, a is positive, b is positive, and additionally a is different from 1. So this gives us an equivalent system, x greater than 0, and also 8 equals 3 plus x over x. Now, because x is not 0, x is positive, we can multiply by x in this equation, both sides, to get 8x equals 3 plus x. That simply means, by adding negative x to each side, that 7x equals 3. And 7x equals 3 is equivalent to x equals 3/7. That is, of course, logically equivalent to x being 3/7. Now, in the second part, we're asked to sketch both functions and understand if our sketch is consistent with what we just found. We found that the two curves, the two graphs, intersect at the point whose x-coordinate is 3/7. All right, so what do we know about these two graphs? Of course, both are obtained by a graph transformation from the base graph log x base 2, namely, the graph of 3 plus log x base 2 is the result of shifting log x base 2 vertically by 3 units up, and the graph of the other function, log 2, 3 plus x, is the result of shifting log x base 2 by 3 units to the left. So if I add a new page, and draw them on ruled paper, so let's first draw log x base 2. Passes through the point 1, 0. At 4, the value will be log 4 base 2, that's 2. Now, if we shift it by 3 units upward, it'll be, by 3 units upward, it'll be the graph of log base 2 of x plus 3. So that's 3, that's 4, that's 5. So the graph will look like this. Of course, they don't intersect. And the other graph, log base 2 of x plus 3, will look the following way. So it will be shift of log base 2 of x horizontally by 3 units to the left. So that'll be a graph whose vertical asymptote is x equals negative 3. Well, in my picture, yeah, it may be 3/7. Okay. Although it looks more like 1/2, but this here supposedly is 3/7. Of course, the purple and the orange graph don't intersect either. And again, this point here supposedly is 3/7. So we can confirm that these two resulting graphs do intersect at the point consistent with the previous solution, x equals 3/7. And one more time, when you solve logarithmic equations, make sure not to forget to keep track of the conditions that ensure that all the logarithms involved in your equation actually exist. That's very important. If you don't do that, you might get some extraneous solutions. This problem is now over.